But I don't have much patience for anyone who denies that this challenge is real. We don't have time for a meeting of the Flat Earth Society.
You see, when public figures begin mocking certain ideas, that's when you have to begin looking into that idea, because most likely there is some truth in it. So with this hype about
Modern high-performance aircraft require electric gyroscopic instruments. The turn and slip indicator, the attitude indicator, and the directional gyro. These electric instruments are dependable at extremely low pressures and temperatures, where gyro suction instruments are unreliable. This film will explain the theory of operation of some of the newer electric gyroscopic instruments. To understand any gyroscopic instrument, you must understand the principle of the gyroscope. It consists of a rotor mounted in a gimbal. The rotor can spin in one plane only. When another gimbal is added, a second plane of movement is possible. And when this assembly is mounted in bearings, the rotor has 3 planes of movement and can assume any possible attitude. This is now a freely mounted gyroscope. A spinning gyro has 2 important properties: precession and rigidity in space. All of its practical applications are based on these 2 properties. As for rigidity in space, the spinning rotor remains in its original attitude, while the gimbals and base move around it. In other words, the gyro maintains its axis in relation to space and not to the surface of the Earth. If a gyro moves around the Earth, its axis is vertical to the Earth's surface.
You should be able to predict the angle that the gyroscope will rotate over a given time at a given latitude. This notion has been accepted as fact by modern-day science without a shred of evidence to support it. Nowhere can I find any video that demonstrates this apparent proof. I found the same assertion made about apparent drift all over the internet, including on aviation websites like this one, which gives more illustrations and the same equations for calculating the drift. My experiment / demonstration, which is coming up next, will be done using the Super Precision Gyroscope. These are manufactured here in England, and if you haven't guessed by the name, they're works of precision engineering to exacting standards. Here's a video by the manufacturer.
At last, a gyroscope that just works properly, just like you've always wanted. Novel, innovative, and precise. The fascinating properties of gyroscopes, with their ability to maintain position and seemingly gravity-defying properties, will mesmerize both young and old alike. The Super Precision Gyroscope is beautifully designed and manufactured to the highest precision. The gyroscope comes complete with its own electric starter motor. There's no need for string to start it. It's less fiddly, spins the gyro much faster, and doesn't put load to the delicate bearings. Even when spinning at 12,000 revolutions per minute, there is hardly any noise or vibration. And when it's up to full speed, it spins for a very long time. The gimbals are modular, allowing you to construct numerous configurations. You can build the standard setups to demonstrate nutation and precession, plus you can make your own setups to perform your experiments. The parts screw together, as well as 7 places around the gyroscope frame. It will provide hours of amusement and learning by showing just how gyroscopic forces affect our daily lives. Today they can be found in aircraft, satellites and many other guidance systems. Made from solid brass, aircraft-grade aluminium and stainless steel. All of the components are precisely manufactured with state-of-the-art machines. We use some of the most accurate equipment available to detect the slightest imbalance. The brass rotor is dynamically balanced to within a few thousandths of a gram and assembled with ultra-low noise bearings. This meticulous attention to detail produces a true precision instrument that will last for years. The set includes the super precision gyroscope with electric starter motor and gimbals kit, complete with manuals and storage case. Our gyroscope is ideal for schools, universities, or anyone who just enjoys using well-engineered kit. It also makes a great gift for those with inquisitive minds.
Okay, so this is the setup I'm going to be using. You'll notice this side, there's like a blanking insert that goes into the bearing housing on this side. And on this side you attach the motor, so the hole is empty, just with the spindle sticking through. So I quickly realised that when I spun this thing up, due to the presence of material here and the absence of material here, there was a weight imbalance. So I contacted the manufacturer and asked them if this is expected, and they confirmed it was and offered to make me a one-off insert to go in here for free. But they also suggested that what I could do is use some Play-Doh, some kids' plasticine. So I did that. I got some of my daughter's Play-Doh, just spun it up to speed with the motor and then inserted this into the hole. That seemed to do the trick. I was able to balance it perfectly. Before I put this in, the extra weight caused this side to drop every time, and if it was over here it would drop this way. So that's how I overcame that. I've attached the whole setup to a protractor which I've blue tacked to the table, and I've blue tacked the actual the frame to the table as well. So this here is the angle that we're looking for. So what we're looking for is this effect. See how the gyro wants to rotate and stay in the original orientation? Well, that angle that it's rotating, that this bar appears to be rotating over the vise, that is the angle that we're looking for. That is the angle that we should be able to calculate this gyroscope moving due to the rotation of the earth underneath us. So without further ado, let's get on to the test. So I've just attached the motor there. It actually takes 4 AA batteries to power it, and I've run this test quite a number of times now and put quite a few batteries through it, so I kind of know how long they're going to last and what sort of sound comes from the motor, depending on how much power is left in the batteries. And I'd say there's about probably 75% power left in them at the minute, and that's based on 12,000 RPM maximum. That's probably about 8,000 or 9,000 RPM for this particular test. So it's getting up to speed now. We're going to remove the motor and replace it with the piece of Play-Doh to get it perfectly balanced. And now I'm going to demonstrate some precession by gently pressing on the horizontal bar there. And now I'm going to line it up as best I can, so that you cannot see the brass flywheel from above, and it's as sort of straight up and down as possible. So if we just take note of where we are now, you can see a 0 on the top right, just to the right of the bar. You can see a 0 just there, and you'll note that you cannot see the brass flywheel from above now. So we are sort of dead centre above it. So now it's just a waiting game. So while we wait, let's just have a look at a brief history of the gyroscope, up to the point where it was first proposed that it could record the spin of the Earth. So this is just sort of one example that I found on the internet. There are lots and lots of different accounts and they all differ slightly, but this one seemed like a sort of all-round recount of history. So in early times, people discovered the spinning top, a toy with a unique ability to balance upright while rotating rapidly. Ancient Greek, Chinese and Roman societies built tops for games and entertainment. The Maori in New Zealand have used humming tops with specially crafted holes in mourning ceremonies. In 14th century England, some villages had a large top constructed for a warming up exercise in cold weather. Tops were even used in place of dice. It was not until the late 18th and 19th centuries that scientists and sailors began attempting to use spinning tops as a scientific tool. At the time, sailors relied on sextants for navigation, measuring the angle between specific stars and the horizon. This method was limited, however, if choppy seas or fog obscured the true horizon, or clouds obscured the stars. Serson, an English scientist, noted in the 1740s that the spinning top had a tendency to remain level, even when the surface on which it rested was tilting. He suggested that sailors could use it as an artificial horizon on ships. Unfortunately, when Serson went to sea to test the idea, the ship sank and everyone was lost. A French scientist in the 19th century, Fleury, created a top that was continuously powered by air jets, blowing into mini buckets on the rim of the wheel, a process that had been used for thousands of gyros since. The first modern gyroscope was designed in the early 1800s by Johann Gottlieb Friedrich von Bernberger, a professor at the University of Tübingen in Germany. It was made with a heavy ball instead of a wheel, but since it had no scientific application, it faded into history. In the mid-19th century, the spinning top acquired the name gyroscope, though not through its use as a navigational tool. French scientist Léon Foucault had experimented with a long, heavy pendulum in an attempt to observe the rotation of the Earth. The pendulum was set swinging back and forth along the north-south plane, while the Earth turned beneath it. Foucault corroborated the observation by using a spinning top in a similar manner. He placed a wheel, rotating at high speed, in a supporting ring in such a way that the axis of the spinning wheel could move independently of the ring. In fact, the supporting ring moved over the course of a day, as it was connected to the surface of the rotating Earth. The axis of the wheel remained pointed in its original direction, confirming that the Earth was rotating in a 24-hour period. Foucault named his spinning wheel a gyroscope, from the Greek words gyros, which is revolution, and scopin, which is to see. He had seen the revolution of the Earth with his gyroscope. So, from Wikipedia, Jean-Bernard Léon Foucault, born 18th of September 1819, was a French physicist best known for his demonstration of the Foucault pendulum, a device demonstrating the effect of the Earth's rotation. He also made an early measurement of the speed of light, discovered eddy currents, and is credited with naming the gyroscope, although he did not invent it. Foucault was the son of a publisher in Paris, where he was born. After an education received chiefly at home, he studied medicine, which he had abandoned in favour of physics due to a blood phobia. He first directed his attention to the improvement of Louis Daguerre's photographic processes. For 3 years he was experimental assistant to Alfred Donné in his course of lectures on microscopic anatomy. In 1851 he provided an experimental demonstration of the rotation of Earth on its axis and became well known to the public by Foucault's work. Foucault achieved the demonstration by showing the rotation of the plane of oscillation of a long and heavy pendulum suspended from the roof of the Pantheon in Paris. The experiment caused a sensation in both the learned and popular worlds, and Foucault pendulums were suspended in major cities across Europe and America, attracting large crowds. In the following year, he used and named the gyroscope as conceptually simpler experimental proof. In 1855 he received the Copley Medal of the Royal Society for his very remarkable experimental researches. In 1862 Foucault was made a member of the Bureau de Longitudes and an officer at the Legion of Honour. He became a member of the Royal Society of London in 1864 and a member of the mechanical section of the Institute a year later. He is also credited with determining the speed of light to be 298,000 km per second, which is only 0.6% in error of the currently accepted value, and devising a method of testing the mirror of a reflecting telescope to determine its shape. So reading between the lines, he was a man of significant academic accomplishment and recognition at the time. One has to wonder then why, when you read the Wikipedia article about Leon Foucault, does it have this one line at the end? Near his death, he returned to Roman Catholicism that he had previously abandoned. Draw your own conclusions. So going back to the test, we've exceeded 6 minutes now and there's no observable movement. You can still see the zero to the right of the bar in its entirety, and you still cannot see the brass flywheel from above. So how much should the gyro have precessed? What angle should the gyro's axis have moved? The calculation is the sine of the latitude times 15 degrees per hour. My current latitude is exactly 53.06 degrees north. So the angle in which the gyro should have moved in 6 minutes is 1.2 degrees. Now this doesn't sound a lot, but let's assume that Leon Foucault's experiments were performed in Paris. He should have seen even less based on his latitude. And let's not forget that he didn't have an electric motor spinning his gyro up to 9,000 RPM. So I'm just going to stop it now. You saw then that there was still plenty of energy left in that flywheel, and it was able to precess when I moved it. So out of sheer curiosity I decided to fix the motor to the gyro and put a counterweight on the other side, which is slightly heavier than the motor, so I counterweighted the counterweight with more Play-Doh until I got it perfectly balanced, and ran the motor for, I think it was 10 minutes on this one. I'll show you a few minutes of it, but I'm not going to show the whole lot. If anybody wants me to, I can upload the whole video. It's pretty boring, it just does nothing. But this is now the equivalent of, I guess, modern navigational aviation instruments, with sustained rotation. In Foucault's tests, the rotational velocity would have been continually decreasing. If the batteries are fully charged, I can actually get about 19 minutes of sustained rotation once I've taken the motor off, which is a hell of a lot on this gyroscope. I did actually try putting the motor on and keeping it on and just running it, I think it was for about an hour with a full set of batteries, and still I observed absolutely no movement whatsoever. So it appears that whether you've got the motor on or you've got it up to speed and then taken it off, it doesn't matter, it still doesn't move. So I just cut to 10 minutes. Like I say, if anybody wants me to upload the whole 10 minutes, I will. Or if anybody wants to see me put it through for an hour with the motor on, I'll video that and show you no movement as well. Bearing in mind that after an hour it should have rotated at about 12 degrees. These are some of the gyros that Leon Foucault used in his experiments. The large one at the back on sort of the wooden tower was a later addition. That one wasn't manufactured until 1867. But the ones at the front were all part of the same setup, and they were demonstrated in 1852, so 15 years earlier. And what you do is you take the flywheel out of the gimbaled, the brass gimbal stand on the right, and you place it in this wooden sort of housing and spin it up. Quite how it was spun up isn't clear, I couldn't really find that out, but once it's up to speed, they then take it out of this wooden frame and transport it back into the brass gimbal set, then you see the long pointing arm, the white pointing arm, coming from the sort of axis, the rotational axis there, onto the little measuring stand, which would have had graduations marked on it. And then with the eyeglass, he would look through it and see what the sort of rotation is. So you can see what we're looking at is a very, very tiny amount, and that's due to the fact that he couldn't spin his gyro up for very long back then. Some of the sources I found said it was only between 150 and 200 RPM, which I'm sure doesn't sound right, because I think I could spin that up quicker with a piece of string wrapped around the spindle. But that's what it says. So he wouldn't have had long to actually get this reading before the gyro slowed down to a stop. What, maybe 3-4 minutes? Let's give him the benefit of the doubt and say 5 minutes. So based on a latitude in Paris, that's less than 1 degree's movement in 5 minutes. So you can start to see why he needs the extended arm to sort of exaggerate the angle, and the sort of magnifying telescope looking device, because the movement is extremely small. Now this movement could purely be down to a weight imbalance like I had, or it could be the friction in the bearings. Remember, this was 1852, technology wasn't as it is today. If you remember on the manufacturer's video, they said that there's absolutely no load on these bearings. So whether he was lying about seeing any movement, or whether he did see some movement, but it was just due to the inferior setup he had, I guess we'll never know. Now some of you might be thinking, aircraft directional gyros do actually drift, and this is true. The pilot has to realign the gyro compass with the magnetic compass every 15 minutes. That's good practice, I know that from personal experience. And this is said to happen because of apparent drift. They say it quite clearly in the 1960s US Navy video that I've linked to. They blame this completely on apparent drift. But I'm going to try and simulate what I think is happening, and why pilots have to realign the compass every 15 minutes. So what I've done is I've aligned the vertical peg here with the vertical casing of the gyro there, and I've aligned it, this bar, the bottom bar there, with this foot here, with this third foot. So I'm going to simulate turbulence, vibration from the aircraft, track changes, by just wiggling this bar. So this is only a gradual thing. Every 15 minutes it drifts out slightly, and it varies as well. Sometimes it drifts quicker than other times, and as pilots will be aware, after any sudden or hard banks, or sort of large turns, the compass seems to drift even further and quicker. So let's realign the... it's not been doing it for long enough yet. Let's give it a few more. There you can see it's already drifting that way, and it doesn't matter which way, it just depends on the bias of the turn, or the bias of the number of turns in any particular direction. It will tend to drift that way. Now you can see, look, it's gone quite a long way out now. So that's what I think accounts for the corrections that the pilot must make every 15 minutes to realign the gyro compass with the magnetic compass. And what of the artificial horizon? That's a gyro as well. Why doesn't that need resetting every 15 minutes? Surely that would be subject to the exact same drift as the directional gyro. But it's actually considered bad practice to realign your artificial horizon during flight because you don't know whether you're aligning it to a straight and level orientation. So why does the directional gyro drift but the artificial horizon gyro doesn't? Well, I believe it's because the directional gyro is 2-axis, so it's allowed to move this way and it's allowed to move this way, but if it moves this way, the actual flywheel moves with it. In a 3-axis gyro, it can actually move this, the axis can move this way, but the gyro flywheel stays aligned like this. But logically, if the directional gyro precesses due to wanting to remain rigid in space, the artificial horizon gyro would necessarily have to do the same, but it doesn't. So for all the naysayers out there who think I might be somehow deceiving or I'm doing something wrong, be my guest. Get yourself a gyro and demonstrate it rotating or appearing to rotate to the exact angle, because it should work like clockwork. If you're not willing to do that, then you are just accepting the word of some dude that performed an experiment 164 years ago that you've never witnessed yourself and nobody else alive today has ever witnessed. After all, it's a really easy experiment. All you need to do is get a perfectly balanced gyroscope, set it running and wait. You can't really do much wrong. Thanks for watching.
An angle here and horizontal here. The gyro will resist any force that attempts to change its plane of rotation. This leads to the principle of precession. When a downward force is applied here, the gyro moves, but not in the direction of the applied force. Instead, it moves at right angles to the applied force. This action is known as precession. If an upward force is applied at the same place, the gyro again precesses at right angles, but in the opposite direction. The explanation is simple. The rotor is spinning in this direction. When the force is applied, the gyro precesses in a direction to align the direction of rotation with the direction of the applied force. The rate of precession is in direct proportion to the applied force. Small force, slow precession. Greater force, faster precession. If enough force is applied, the gyro precesses a full 90 degrees. However, at or near 90 degrees, it will tumble and go out of control. This disadvantage must be overcome in gyro instruments. Another disadvantage comes from the gyro's tendency to drift away from its original attitude. There are two types of drift. One is mechanical, due to friction in the bearings. This is actually a form of precession. The other type, known as apparent drift, relates to rigidity in space. Once again, consider this condition. The gyro maintains its attitude while the Earth turns under it. Every 6 hours, the gyro drifts through 90 degrees in relation to the Earth's surface. In order for the gyro instrument to be dependable, drift must be corrected continuously. There are several types of erection systems that correct for drift. The principle back of all these systems is based on 3 steps. The direction and degree of drift are measured by electrical or mechanical sensing elements. These elements then control the application of a proper force to the gyro, and it precesses back to its normal attitude. All gyros in this film are actually the rotors of electric motors. However, for simplicity, we will represent them like this, this, and this. We will start with the turn and slip indicator. It is really two instruments, each of which provides the pilot with information during a turn. This needle shows how much the aircraft is turning. This ball shows the kind of turn the aircraft is making. We will examine the turn needle first. It is actuated by a gyro, which is mounted in only one gimbal and in bearings that are secured to the case. The gyro can turn about the fore and aft axis, but not about the vertical axis. A spring restrains any movement of the gyro from its normal attitude. The gyro is linked to the turn needle like this. We will see how the property of precession is used to indicate the aircraft's rate of turn. When the aircraft turns to the right, forces are applied at the gyro bearings here and here. The rotor is spinning in this direction, so the forces cause it to precess in this direction. The linkage moves the needle in the direction of the turn. When the force of precession equals the spring tension, the needle indicates the rate of turn, as well as the direction. When the aircraft levels off, the spring erects the gyro to its normal attitude, and the needle returns to zero. A dampening piston and cylinder are linked to the gyro to steady any precession and prevent hunting by the needle. The ball is independent of the gyro. It is free to move back and forth in a curved tube. During straight and level flight, the force of gravity holds the ball in the center of the tube, and the aircraft is in balanced flight. During a turn, two additional forces affect the ball: horizontal lift and centrifugal force. When these two forces are equal, the aircraft is in a balanced turn, and the ball remains in the center of the tube. When the centrifugal force exceeds the horizontal lift, the aircraft skids, and the ball rolls toward the outside of the turn. When the horizontal lift exceeds the centrifugal force, the aircraft slips, and the ball rolls toward the inside of the turn. We will examine two attitude indicators, the H6 horizon indicator and the vertical gyro indicator. Each instrument continuously indicates the roll and pitch attitudes of the aircraft in relation to the actual horizon, and each obtains this information from a freely mounted gyro. The axis of the rotor is vertical and, due to the property of rigidity, will remain in this position as the aircraft assumes any attitude. Therefore, the gyro establishes a vertical reference from which roll and pitch deviations of the aircraft can be measured. It is unnecessary to cage the gyro in either instrument during any maneuvers. We will start with this one. This miniature plane represents the aircraft, and this bar represents the horizon. The horizon bar is mechanically linked to a gyro mounted in the case. The two supporting arms are connected to pivots at the rear of the outer gimbal and by pins to the inner gimbal. When the aircraft climbs, the gyro remains erect, while the aircraft and case move around it. This action lowers the horizon bar below the miniature plane. The instrument now indicates the aircraft's present attitude relative to the horizon. At plus or minus 27 degrees of pitch, the horizon bar reaches mechanical stops and ceases to give any further indication of pitch up or down. Some models of this instrument have a scale to indicate pitch to 80 degrees plus or minus. In addition to the horizon bar, this pointer is secured to the outer gimbal of the gyro. It is used with these fixed markings on the case to indicate the degree of roll. When the aircraft rolls, the gyro remains erect and holds the pointer in this position, while the horizon markings roll around it. The degree of roll can be read here. The pilot can use these knobs to adjust the positions of the miniature plane and horizon bar manually. Since the gyro is linked mechanically to the horizon bar and pointer, the dial must be mounted in a vertical position. This model of the attitude indicator has a fixed miniature plane and roll markings on the instrument face. Back of the dial face is a sphere representing Earth, sky, and horizon, with 5-degree markings for climb and dive. It is universally mounted, so it can rotate around this axis 82 degrees in either direction, and can roll 360 degrees around this axis. This pointer can move only around the roll axis. A remotely mounted gyro controls the sphere through 2 electric circuits, one for roll, the other for pitch. A position transmitter is in the roll axis of the gyro, and another is in the pitch axis. They connect through receivers and amplifiers to the servo motors that drive the sphere in pitch and roll. Assume the aircraft rolls 30 degrees. This transmitter measures the roll displacement of the aircraft from the vertical reference. This measurement, in terms of a small voltage, goes through the receiver and amplifier to the roll servo motor, which turns to position the sphere and pointer. The degree of roll is indicated by the pointer and roll markings. Assume the aircraft climbs at a 30-degree angle. This transmitter measures the angular motion in terms of a voltage. The amplified voltage drives the pitch servo motor, which turns to position the sphere. The degree of pitch can be read on the horizontal markings back of the miniature plane. When the aircraft reaches 82 degrees of pitch, the gyro goes through a controlled precession of exactly 180 degrees. As a result, the sphere also exactly reverses its position and continues to indicate the aircraft's changing attitude. This knob can be used to position the sphere electrically. The dial can be installed at any angle because the gyro is not mounted in the instrument case. We will examine 2 directional compasses, the C1 directional gyro heading indicator and the MA1 compass system. And we'll start with this one. The aircraft's heading is indicated here, and the reciprocal heading here. To obtain this information, the instrument uses a freely mounted gyro. Due to its property of rigidity, the spin axis of the gyro will hold its attitude as the aircraft and instrument case turn about it. Secured to the outer gimbal is a gear. Its teeth mesh with the teeth of another gear, to which the compass card is attached. Before it can indicate correct headings, the compass card must be set to the heading of the aircraft, as indicated by the magnetic compass. The push-to-cage knob is used to make the setting, after which the gyro controls the compass card. Assume the aircraft makes a 90-degree turn. The instrument case turns around the gyro and lower gear. As a result, the vertical gear makes a quarter turn as it travels around the lower gear. So the compass card also makes a 90-degree turn. Any climb or descent will not affect the compass card unless the heading changes. However, If the pitch or roll of the aircraft exceeds 60 degrees, the gyro will tumble and may be damaged, and the instrument will give inaccurate readings. Therefore, when entering a maneuver that may exceed the limitations, the gyro must be caged. The instrument will be safe, but out of operation. When the maneuver has been completed, the magnetic compass heading must be set into the instrument again. In this instrument, apparent drift causes the compass card to drift away from its heading about 3 degrees every 15 minutes. And so, every 15 minutes, it must be reset to the magnetic compass heading. We have seen that a gyro is stable and accurate for short periods of time, but is subject to long-period drift. In contrast, a magnetic compass is accurate over long periods, but subject to short-period instability and oscillations. The magnetic compass is particularly accurate between 60 degrees north and south latitudes. But near either of the poles, the dip angle of the Earth's magnetic lines of force causes this compass to become unstable. The MA1 compass system combines these two instruments into one system that uses their advantages and eliminates their disadvantages. The magnetic compass, in the form of a flux valve, is mounted remotely in the tail or wingtip, away from the worst magnetic disturbances within the aircraft. The gyro is also mounted remotely from the indicator dial. The system is designed for two modes of operation. In the free gyro mode, the gyro alone controls the indicator dial. In the slaved mode, the magnetic compass controls the gyro. We will first examine the slaved mode of operation. We will represent the flux valve as a magnetic needle mounted on the rotor of a synchro transmitter. The needle will remain aligned with the Earth's magnetic field while the aircraft turns in any direction. The stator of the compass transmitter is connected electrically to the stator of a synchro control transformer. The gyro's outer gimbal is mounted on the rotor of this synchro. When the outer gimbal is properly oriented to the magnetic needle, there is zero output from the control transformer. But if the aircraft changes heading or the gyro drifts around the vertical axis, the outer gimbal is not properly oriented. The control transformer immediately sends an error signal through an amplifier to the torque motor mounted on the inner gimbal. The torque motor applies the proper torque to the inner gimbal, and the outer gimbal precesses to proper orientation with the magnetic needle, at which time the error signal is canceled. The magnetic needle may oscillate and send an oscillating signal to the gyro. However, the gyro's rigidity in space is such that it does not respond quickly to slight changes in the needle. Instead, it aligns itself with the average position of the needle. Mounted above the gyro is a synchro transmitter, which continuously measures the deviation of the gyro case from the outer gimbal. It transmits this information to the indicator dial, where another synchro positions the compass card to indicate the aircraft's heading. Thus, in the slaved mode of operation, the gyro is a drift-free, stable indicator of magnetic direction. In the free gyro mode, the flux valve is disconnected from the gyro. When the gyro is oriented properly, it tends to hold that orientation. However, it is subject to apparent drift, which increases as the gyro approaches one of the poles. Apparent drift is corrected automatically by latitude compensation circuit. The aircraft's latitude is set manually into the system and changed whenever necessary. This sends an appropriate and constant voltage to this torque motor. The motor applies a constant torque to the inner gimbal. As a result, the outer gimbal precesses constantly at a given rate to offset the apparent drift. and the gyro sends accurate directional information to the indicator dial. Electric gyroscopic instruments are dependable at the low atmospheric pressures and temperatures in which modern high-performance aircraft must operate.
Take that off, turn the motor off, and come on, there we go. So I've got that spinning really fast, 12,000 RPM according to the manufacturer, and I want to put out a challenge, and that is that I'm prepared to post this gyroscope out to anybody who believes that the Earth spins and that Leon Foucault's experiments back in 1852 were legitimate and not flawed in any way, and they believe that this can be demonstrated using a gyroscope. So I will post this out, including all the little accessories that you get for the gimbal, the counterweight, some of the accessories, the electric motor, and the deal is that I'll give you, say, 30 days from receipt of the gyroscope to put out a video showing the apparent drift due to the rotation of the Earth below us, to the exact exact angle according to your latitude on the Earth. It must be precise, and it must be videoed and put up on YouTube. I would like it back after 30 days, regardless of whether you can or can't replicate the outcome. So I've had 33,000 views on the first video, and nobody yet has come back and showed me any proof, demonstrated anything to the contrary. You would have thought it would be pretty easy. This was a known problem, or it's apparently a known problem. It's inherent to all gyros. They all exhibit this apparent drift due to the rotation of the Earth. Yet, from the couple of people who have demonstrated this so far on YouTube, haven't been able to replicate it. I mean, somebody must be able to replicate it. It's apparently a known problem, and different technologies such as Schuler tuning have been invented to overcome it. Well, this gyroscope doesn't need any Schuler tuning because it can't be replicated, and we all know that science is all about replication, repeatability. If it can't be repeated, it's not science. So there's the challenge right off the bat. I'll pay for postage. You're getting a gyroscope for absolutely nothing to demonstrate it on. If you don't think this one's suitable, then let us know which type of gyroscope you do think would be suitable. I will purchase it, as long as it's not too much money. I'll test it, I'll send it to you. You can test it. We'll see if there is any validity to this at all, because from the results I'm getting, there is none. So one of the problems that somebody came up with is that this is just a toy. I don't know, this here is just a toy. This is a toy gyroscope, and I'll spin it up now. So, you see this is still moving. And we'll see what the difference is between a toy and a piece of precision engineering. And so, what else? Yes, in my first experiments I didn't clarify which direction the gyroscope was aligned, whether it was north, south, east, west, somewhere in between. I can confirm that it was, in both experiments, it was 140 degrees or 320 degrees, depending on which way you look at it. So it was southeast or northwest, depending on which way you looked at it. In one experiment the camera was this side, on the other experiment the camera was this side, so it was 180 degree opposed from each other. Not that makes or should make a difference according to the sources I've been using, which is a website called theairlinepilots.com. They've got a page dedicated to it explaining all the maths. They don't mention the orientation, north, south, east or west. All they say is that this is dependent on, you can see this has stopped now, this is still going. All they say that it's dependent upon is the orientation of the gyro, whether it's vertically aligned or horizontally aligned, and that refers to the spin axis of the gyro. So here's the spin axis, this is vertical, this would be horizontal, like that. So if it's horizontal like this, the calculation is 15 times the sine of the latitude in degrees per hour, and if it's like this, it's 15 times the cosine of the latitude in degrees per hour. So it doesn't mention anything about the particular direction that these are in. Another problem somebody had was that the duration that I tested it for wasn't long enough. I tested it in this sort of configuration without the motor. I tested it for 6 minutes, just over, and it was supposed to move 1.2 degrees in them 6 minutes, but it didn't move at all. I'm not sure what testing it for any longer would have achieved. If it didn't move 1.2 degrees in 6 minutes, it's not going to, if I run it for an hour, it's not suddenly going to jump. So I'm not quite sure what the problem is with that. Besides the fact somebody else has repeated this since I did it, and they've done it for an entire 6 hours, and they've uploaded the whole 6-hour video to YouTube. So I'm going to link to all these sources in the description. What else? In the powered experiment that I did, somebody said that the fact that this has got a wire on it was sort of the wire here was acting as an anchor and preventing it from turning. Now that could be a factor, I do agree. However, I have tested this quite a lot, and this I did leave it quite slack on mine. So if it did want to move, it could have pulled it, and these are perfectly capable of pulling them. Some people have said that they don't believe the torque is enough to overcome. They don't believe the torque is enough to overcome the friction in the gimbal set here and here. This movement here. However, in the experiment, I did demonstrate using a turntable that I was manually spinning. I know it was faster than what the Earth supposedly spins, or not, maybe. But relatively speaking, it was faster. But it was still, you could still see it moving. I'll show you again what. I'll repeat it here now, so you can see it. Some people said the calculation was wrong. Well, I've told you where my source was. If somebody can tell me a different calculation and point a source to it, please do. But regardless, the gyro is supposed to drift. What difference does the calculation matter if it was right or wrong, as long as it wasn't supposed to rotate sort of 0.001 of a degree, and over the time I tested it for, you wouldn't have been able to see that. That's the only sort of way that the calculation could have had any bearing on it. But like I say, I've told you where I got the calculations from. It should have moved 1.2 degrees, but it didn't. What else? Yeah, I just wanted to point out that to make a good gyro, there's 3 properties required. One is a high rotational velocity, or high angular velocity of the flywheel. The faster it's spinning, the better the effect. The second property is that the flywheel needs to be perfectly balanced. It will spin much longer if it's perfectly balanced. And then obviously the third is to have low loss or low friction bearings, all of which this particular gyro has. Otherwise it would not still be spinning right now. one of the flaws from Foucault's experiments that I've discovered that probably played a part in it is that as these things are spinning down, the precession is less precise. You can see now, look, it's still spinning and it will still precess. You see? However, because it's spinning so slowly, there are some times when I can actually move this and it won't move. And that's because it's spinning slowly now. So as Foucault's gyroscope was spinning down, as the Earth was supposedly spinning underneath, and this was doing this, it was giving it this sort of, you can see it's not moving at all. It's not actually moving at all. However, if I give it a quick, there you go. It tends to do this when it's spinning much slower. When it's spinning at full speed, there's no delay in this whatsoever. It's very, very precise. You move this and it moves that instantaneously. And this thing will spin for 19 minutes from if I don't mess around with it, because every time you move it slightly, it takes some of the energy out of the flywheel. If I leave it spinning without moving it, after powering it up with the motor to full speed, it will spin for 19 minutes. That's what I've timed it for. When I was flying a Robinson R-22 helicopter, if I landed it, turn the engine off, turn the electrics off, the gyro in there, you can hear it still spinning. It would spin for about 10 minutes before it toppled over. This spins for longer than the gyros in the R-22 helicopter. So this should, for all intents and purposes, this should be a perfect demonstration tool to replicate what Leon Foucault did. It looks very similar to what the apparatus he used as well in the configuration that I've got it. The other thing I would like to point out is the Foucault's pendulum. The same guy that proposed that a spinning gyroscope could demonstrate the Earth spinning, he also proposed that a swinging pendulum could also have the same effect. And it is virtually the same analog. It's the same thing. It's the same sort of principles demonstrating the same effect. Now I've never actually seen a Foucault's pendulum. I've never witnessed one working. I would like to, but there's none nearby to where I live. But I don't think it'd be too difficult to replicate a Foucault's pendulum. What you need is a really tall building, and I'm sure there's somebody out there who's got access to a really tall building. And I'm thinking something like an old bowling ball, if you don't mind, drilling into it to fix an anchor point into it. And all you need is a piece of thin steel wire and some sort of way of attaching it at the top so that it's free to spin in any direction. It doesn't have to be brass. The common ones that are in museums and everything, they're all made of brass, and although not publicly mentioned on places like Wikipedia, brass is very, very slightly magnetic. I can get a tiny little neodymium magnet, and I can stick it to my brass flywheel on this gyroscope. So I think that the brass in the Foucault's pendulum has something to do with why they're spinning. I've mentioned it in previous videos. It's a theory of mine. So I'm thinking that if we use a bowling ball with no magnetic properties, no ferrous magnetic properties to it, and we test that, we might get some different results. As you can see, this thing is actually still spinning very slowly now, but let's see if we've still got some precession going on. So if you are up for the challenge, any spinning Earth proponents out there who would like to have a go at debunking this, showing some sort of spin, using either this gyroscope or any other gyroscope, then please let me know. Thanks for watching.